having an underlying foundation of its ability to do NumPy-like activities directly in the tensors, which allow you to either do the operations on an accelerator or locally on your CPU. Similar to NumPy, except now it's running on your GPU, on your accelerator, which is, wouldn't you rather be doing that kind of math? This is actually kind of neat. If you're going to use NumPy, check this out. If you're going to use NumPy, wouldn't you rather have that running on a GPU, which could be highly accelerated? Now, of course, yes, there are some scenarios where the CPU will actually be faster than your GPU, especially if you're doing a lot of little mini small activities all in a loop, something like that. Although if you rebuilt the algorithm and you had it running on a tensor, it would be a lot faster. Hey, Mark Levin! The type of the object returned is an alias for a float tensor by default. Pytorch tensors are populated with 32-bit floating point numbers. More data types below. It also shows intent. So what you intend to do with it. Okay, so it's got meaning. You're not intending it to be required. Or requited. Requited! You probably see some random looking values when printing the tensor. I didn't though. Torch.empty allocates memory for the tensor, but it does not initialize it with values. Just like you mentioned, never! You know about this already. So what you're seeing is whatever was in memory at the time of the allocation. A brief note about tensors and their number of dimensions and terminology. You'll see a one-dimensional tensor called a vector. Oh, there we go, a vector. Okay. This is actually pretty good for the terminology perspective. A vector, a matrix, an array. Are they all the same thing? Yeah, pretty much. A vector is one-dimensional. A two-dimensional tensor is often called a matrix. 2 dimensions, an x and a y. Anything with more dimensions is generally called a tensor. Yeah, but you can have a tensor with just a single value in it, and it's still a tensor. So yeah, everything's a tensor. I think you can call anything a tensor. More often than not, you'll want to initialize your tensor with some values. Common case are all zeros, all ones, or random values. I like random values. That's my favorite. I like random values. The 2D, 1D terminology is from math. The scalar, Q-scalar is a zero-dimensional tensor. Got it. The scalar, yes. A scalar value, 0 dimensions, which is just one value. Which feels weird, 0 dimensions. I mean, there's something there, but there's no dimensionality to it, right? There's something there, it's a point. 0 dimensions is 1 point. Boop. All right, so we got our zeros, ones, and empties. What else do we got here? Do we have twos? No, we have randoms. Rands equals torch.random 3, 4. Print rands. And then we will have the same thing, except for we're going to have some random there. Ooh, it's nice. I like that. Bongo. What am I missing? We can do ones, randoms. Oh, you can also do a manual seed. I forgot about this. So torch.manual seed 1, 2, 3, 4, 5, 6, 7 operations on 2 or more tensors. They will need to be of the same shape, right? They got to be the same shape. So if it's a 3-dimensional tensor or a 2-dimensional tensor, they got to be the same. Or if you're doing a matrix multiplication or some sort of variant, you need to transpose. Yeah, okay. So we'll do an empty like x. Empty like equals torch.empty underscore like my mat. We'll call it mat. We'll just call it mat because it's a little bit easier to repeat this a bunch of times. Print empty should be identical. Yep, there you go, identical. And it's a little tricky to take a peek at here. So doing that level of dimensionality. Dot ones, oh, zeros, like zeros underscore like mat. Print zeros. Okay. We're keeping it easy today, guys. Keeping it easy. All right. So as you can see, yeah, all 3 are already zeros. We get an empty like, and a zeros like. They're all the same. One's like, and we'll do rand like. Okay. Rand equals torch.rand like mat. Print rand. And now we'll have even more contrast right here. So as you can see, it's the same shape. It's the same shape as it was earlier. There you go. Easy. We're doing a equals torch dot ones. Oh, dtype. Okay. 2, 3, comma dtype equals torch dot int 16. Can we do that? Is that something that works? Print a. See what that looks like over here. You can do an int 16. Can you do an int 8? Or is that me? Or is it gonna be like, no, you can't do an int 8. You can do an int 8. What about int 4? You can do 2. Torch dot int 64. You can do that. That's pretty neat. I didn't know you could do that. Math and logic. All right, let's do some math and logic. All right, so this is great. This is one of my favorite things. Why I like Torch and NumPy, because they let you work on collections of numbers using simple math operators like this. This is why I really like this. Check this out, you guys. This is why I like it. This is why I like it. This is one of my favorite things with Torch. If you guys are ready, check this out. You can do data like this. This is pretty great. This is pretty fantastic. Once you create a matrix, or in this case, it's called a matrix, right? A matrix tensor. You can add 1 to it, and it will apply all the values to every single value. So watch this. Zeros equals torch.zeros. We'll go 3 by 3, so we get a nice, pretty, right? Print zeros. And you'll notice that the data is a bunch of zeros. However, we can say ones equals zeros plus 1. Print ones. And that will apply operation across every single element. Instead of having to do your own for loop, especially with a matrix, it's going to require you to do a nested for loop, right? Oh, we can do a whole bunch of operations here. All right, times 7 minus 1 divided by 2. All right, 3s equals 1s times 7 divided by 2 minus 1. Is this gonna be 3s? There's math, just not enough to make you cry. Yeah, that's a good point. There is, yeah, exactly. There's a smidgen of math. You're right, there's a smidgen of math. All right, so let's print this out. Let's print out 3s. Did we do math right? Did we do math right? I'll feel happy if we did it. It'll be magic accident. Oh, it's not quite 3. Not quite 3. We'll do 9, and then we'll divide by 3, and then we won't subtract anything. Is that 3s? There we go. Hey, we're making our way now. A lot of math lib, graph theory. Some people don't see it as math. Okay, that's fair. That's fair. There's a lot of graphs. 4s and let's see. We'll do 4s next. All right. So 4s equals 1s to the power. What are they doing here? 2. Oh, 2s over here. So 2s times 2. So we could do right exponents. Print 4s. There we go. So now we get 1, 2, 3, and 4. Nice. Oh, it's so satisfying. In between the ranges, however, if the numbers exceed the range, it's going to set a max and min. You do agree? Nice. Very nice, Anasazi. Good to hear it. A, 0.5 and negative 0.5. Can we clamp like that? Is that how we clamp? Are we clamping correct? Let's try again. Do we do it right? We have to start with the bottom. All right, got it. No worries. We just did it backwards. There we go. There are signs and inverse. Sin angles. So we get the sine of the angles. Okay. You can do sine without doing angles. You can. You don't have to do it this way. You can do sines with angles. All right, let's print sines. Let's do some reduction ops. So max, mean, median, standard deviation, prod, and unique. Oh, there we go. Let's try it. Some reduce ops, you guys. Reduce ops. Okay, now I'm happy. Now I'm excited. Leak code is more of a fun game. That's true. Kind of fun. It's fun. It is fun. Friday high day. Yep, you got it. The linked lists. Oh, those linked lists. Yeah, exactly. If AI writes all the code, is there any room for junior devs? Yeah, I mean, Sure. There's plenty of room. Well, all the numbers. That is going to be 24, which is going to multiply each of the numbers, right? So calculator. So if we bring that up, the product of all numbers will be 1 times 2 times 3 times 4. 1 times 2 times 3 times 4. 24. There you go. Product of all the numbers. Very easy, straightforward. Thanks for the actions, you guys. And then we've got unique. Okay, so we got unique. Print torch.prod d is also going to give us the same array back because the numbers are already unique. Wait. Oh, sorry. Unique. UNI QUE. There we go. Unique there. Here we go. Perfect. So it gives us all the numbers that are unique. If we change this up here in the D, so we change this to add another number. We'll like say 2 and 1. We'll see. It'll change the unique. So unique will come back as 1 and 2. There we go. Clear. It was really good. Hey, nice. Good to hear it. Based. We're based, you guys. We're based. We're based. All right. I love this. All right. So that's the at sign. So these are equivalent. So this one, these two are equivalent here. This one's a little bit different. Okay. Let's try it again. So we should see identical. Yep. There we go. Identical. So you can either draw it out like this with a lot of text, or you could just use the at sign. Did mult, and we'll do SVD. Singular value decomposition. Print. Here we go. We're going to say torch.linearalgebra.svd, and we're going to do it on M3. There we go, you guys. And so we did it. Oh, we got ourselves some numbers. I don't know what you do with that. Do you know what IKEA HQ has moved to the Netherlands for tax reasons? Oh, what? They're not in Sweden anymore? Wait, it's a Swedish. It was originally in Sweden, right? Even North Korea has IKEA. Do they really? Von Zupi? I had no idea. All right, altering tensors in place with the underscore operator. Yes, underscore operator. We knew about that. We knew about that, guys. It's Swedish. Yeah, it was Swedish. All right, you guys. We're getting into the weekend now. Wait, let me double check. Okay, we'll let you double check. So if you guys wanted to do a mutation operator, you can use the underscore. It doesn't work for every method. It works for some of the methods. Not every single one. All right. So I'll show you. Okay, so can you do that on, for example, where would that work? So we've got a sign. We'll do this here. Okay. So we got a 3. Let's hide these here. We'll hide this. There we go. Hide. Keep things hidden. All right. No. Yeah, we don't need. Okay. So we'll print 3, and then we will show you print. So we'll do m3 torch.sign underscore m3. Okay. Check general.